Excellent. So welcome back, day 4. I just want to say at the front end here that we're going to try and spend the last half an hour, so we're going to reserve the last half an hour or so to going over for questions from the audience and general discussion. So as we go along here, if you want to think of a question or identify a key area that you want to have addressed in our final half an hour together, try and think about it now and maybe even write it down. And then when we get to the last half hour, we'll go over that stuff. OK, so for today, we were going to try and start off with a little bit of a discussion about permutation analysis of data, which is something that we were supposed to cover yesterday but didn't quite get to. And then I have a few topics that you can see on the last page that we're going to try and cover today. Some of the stuff that we're going to try and hit on this last day really are overarching conceptual issues in designing fMRI and, in fact, neuroimaging experiments in general. What are sort of manipulations of different cognitive processes, how you might do it, what sorts of inferences you can draw from neuroimaging experiments. So this is really where we're going to take some of the topics we've been considering and apply them in even a more broad sense to neuroimaging in general, not just stuff that's bold fMRI. And then at the very end, we're going to talk about, in that same spirit, a different sort of neuroimaging method, perfusion fMRI, which, although it's also based on an MRI scanner, has quite different noise properties from bold fMRI, so it has different implications for experimental design. So we'll get to that at the end. OK, so first of all, any questions left over from yesterday that we didn't, that left you puzzled overnight that you want to address now? Not too much? OK, well, just to refresh your memory, where we left off, we had talked about random effects and population-level inferences and analyses. And the last thing we had discussed was a group or population-level analysis where you have, in effect, a measure of some task effect from each subject. So here's subject A, subject B, and subject C. And for each subject, you generate a map of the brain where the value at each point in the brain is the effect size of your task, which is derived from an individual subject GLM, which was performed for that subject. So for example, if I was interested in looking at the difference between working memory for objects and working memory for spatial information, I'd have each subject that do a lot of trials with working memory for spatial information, working memory for objects. I'd create a contrast, right? So I'd do the analysis within the individual subject, and I'd create my statistical map, which is the difference, between the covariate modeling, delay, space, subtracted from delay, object. Okay, so that would be my statistical map. And then I'd generate one of those statistical maps for each of my subjects, of course, after their brains had been normalized into a standard spatial frame. And then I would do an analysis effectively across those statistical maps, where I'd say, OK, then for each of my subjects, if I take the effect size at a particular voxel in space, were those values, say, greater than 0. And if they're statistically greater than 0, then that implies that across my population, the neural activity for delay space was greater than delay object. Yeah?
What's the benefit of normalizing the brains rather than just analyzing each individual subject and looking at their t-value for a certain contrast and then doing a one?
T-value for their contrast.
Right.
So the purpose of normalizing the brains, so trying to put different brains into the same spatial register, is if you want to do a statistical analysis across the entire brain, if you want to say across the entire brain for this population of subjects, where was there an effect? But as we saw yesterday, there are examples of experimental questions that you might ask that don't require you to address the data from the entire brain. For example, if I say, here's some anatomically defined area of the dorsal aspect of the dorsolateral prefrontal cortex, and I define that anatomically for each subject, and here is where it is anatomically in my first subject, and here is where it is in my next subject, and this is the other subject. And from each subject, then I sort of derive what the effect was within that region, and then I do a test upon those values that came from that region of interest. Okay, so in effect, I'm testing some notion about an anatomically defined area without ever having to normalize brains. But if you want to do these more sort of exploratory or whole map-wise tests across the entire brain, it is necessary in some way to get the brains into register. So that's why I'd want to do that. Okay. So in general, the effect size that you take from each subject could be a number of different things. You could imagine just taking the raw sort of fMRI signal that's associated with times while they were doing delay space and subtract that from times when they were doing delay object, say, and so then just have from each subject that difference in just raw bold signal. So that would be one thing you could do. The problem is, though, that it turns out the bold fMRI signal can be scaled differently on different days and for different subjects, so that on this day, when the subject happened to be in the scanner, the effect between the two different conditions looked like this, where the values run from, say, 1,000 to 1,050. And then on this day, with this subject in the scanner, the data looked like this, where the values ran from 1,200 to 1,300. Okay? So what can happen is that the overall signal can be sort of scaled up or down. There can be sort of this multiplicative scaling that occurs with bold fMRI data. So what that means then is that even if different subjects had the exact same amount of neural difference between two conditions, the amount of bold signal difference between the two conditions might be variable as a result of this scaling effect, right? So, X units of neuronal difference between the two conditions in all the subjects might yield, 50 units of bold signal difference here, 75 units of bold signal difference here, and 20 units of bold signal difference here. You don't. So the question is there a way to render these numbers a little bit more uniform? And so one way that you might go about trying to figure out, is there a way to measure them, make them more uniform, is to make the assumption that, okay, well, maybe it's the case that within one subject scanned on multiple sessions, or during multiple scans during a session, you would expect this variability in the evoked neural activity to be less than the variability you'd see across subjects. And so then you can ask, what manipulation would I have to perform upon the bold data to minimize the difference in the effect size that I see under those circumstances? And so what you can find is that if you scale these values, say by the intercept term or the mean level, if you scale these values in terms of the mean level of the signal between them, right, or across the measurement, then that has this effect of rendering the effect size more similar across times that you measure it. So this is a long-winded way of saying, basically, that more typically, when we try and enter these data into an across-subject analysis, we use percentage change more typically. So that is the percentage change in the signal evoked by the task. All right, so how much did the signal change from baseline to the activated state in terms not of just raw bold fMRI signal units, but in terms of the percentage amount that it changed? Was it a 1% signal change or a 0.5% signal change or that kind of thing? Okay? So typically that's sort of these scaled values that we enter into the second level analysis. And the reason that's done is to effectively remove or ameliorate the effect of different scaling of effect sizes from scan to scan and from day to day. Okay, any questions about that? It's kind of a bit of an esoteric concept, but at least when you go to make these analyses, you're going to be asked to provide what measure you want to take from each subject. And just so you know, like a percentage signal change would be a typical measure to take. All right. We also talked about how you would assess the significance of the results across your population of subjects. And we were dealing with the case where you had one measurement, right, from each subject. And to keep things simple, let's imagine now you just have you were just going to talk about one voxel for the moment. So you have a single voxel and you have a measurement from each subject. And so the list of measurements, might be 1% signal change, 0.5% signal change, 0.75, 1.2, and so on. So you have a list of measurements across your group of subjects for the percentage signal change associated with the task from that one particular voxel. Okay? And now you want to ask the question, is this list of numbers significantly different from 0? Right? That is, was there a significant effect or a positive effect of your task upon neural activity across the population of subjects? So one way you could easily imagine doing this is just with a t-test. That's straightforward enough. And so simply an unpaired t-test could be performed upon these numbers, and that would give you the answer. Well, it turns out there's somewhat more sensitive ways of doing this kind of thing. And one of the newest and best ways for analyzing data across subjects is to use a permutation analysis. So I'm not going to go into great detail right now about sort of how you do permutations and what it's all about and all the rest. I just want to introduce you to the concept and know that if you're analyzing data across subjects, you probably should be assessing the significance of the result with permutations. How does this work? Okay. The basic idea is that a permutation analysis is used to determine the significance of a result that you have measured some other way. So you would still do a t-test upon this list of numbers, okay? And suppose it came up with a t-value of 3.7. Okay, that was the t-statistic associated with this group of say, 10 values. So you had 10 subjects, so you have 10 values. So t of 3.7 is the t-value that results. Okay, now you're interested in what is the significance of that? What's the p-value associated with that? Okay, so you could go and just look in the back of a statistics textbook and find, okay, well, with 10 subjects, that's 9 degrees of freedom, t of 3.7, that's equal to a p of equal to 0.03 or 2. I don't know. So some p-value. Right? And so you do that by looking up in a textbook and finding out some information about what the t distribution is under the null hypothesis, and that's how you figure out what the p-value is that's assigned to it. A permutation test still starts with calculating this t-test and coming up with a t of 3.7, but now you're going to use a different method to assess its significance. Okay, so instead of going and looking in the back of a textbook to figure out what the p-value is, you're going to try and actually measure the p-value or calculate the p-value. So how is that done? So let's see. Probably the easiest way to think about this is to start with an example where instead of having just one measurement from each subject, you have two sorts of populations. You have two groups. Let's draw this out. Okay, so imagine you have two groups. You have men and women, and you're doing a test looking at working memory in men and women. Okay, so here are your male subjects. Here are your female subjects. And so each of your subjects do the experiment, and you come up with an effect size. That is the difference, between for a working memory effect between spatial and object. You have the hypothesis that women have greater neuronal activity associated with object representation across a delay, and men have greater neuronal activity in prefrontal cortex or wherever associated with spatial representation across a delay. Okay, so you've got some voxel that you define, and an effect across from each of your subjects. Now again, this is subject A, subject B, subject C. So you're going to have a list of values then. So here are your male effect sizes from some region of the brain, the difference between object and spatial working memory. And the values here were for object minus space. In the men, the space effect was bigger than the object effect, so this comes out to be negative 1.2, negative 3, negative 0.2, and 0.10. Okay, so those are the values that represent the difference between the effect of objects and the effects of space for a particular voxel for the male subjects. And for the female subjects, you have the following data: 1.0, 0.75, negative 0.15, and 0.2. Okay, so just by looking at this data, it seems to be the case then that in general in the female subjects, there was greater neuronal activity for the object conditions than the space conditions. In the male subjects, with some exceptions, there was greater neuronal activity for the space than the object. Okay, so how would you assess the significance of this? So one thing you could do is, again, a t-test and compare this population of values to this population of values and ask, is it the case that this group is significantly bigger or smaller than this group? Okay, so imagine you did that and you came up with now a t of 3.2, and in the textbook it says it's a p of 0.02. Okay, everybody with me so far? Anyone have any questions about the sort of the basic conceit of this design? Okay, so but now you want to try and figure out what the significance is in a slightly different way. And in a permutation analysis, what you do is you make the following assumption. You ask the following question. You say, imagine it was the case that my hypothesis was completely wrong. Imagine it was the case that there really is no difference between men and women in this measure that I have. Okay, there really is no difference between men and women in spatial versus object working memory and neuronal activity. Okay? If it were the case that there really was no difference between men and women, it really wouldn't matter how I assigned the label of male or female to any one of these measurements I obtained, right? So what I have here is this measurement came from a guy, man, 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 and these measurements came from female, 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 female. Okay? But if there really was no difference truly between men and women, then it wouldn't matter if this label was an M or an F, right? I would expect there really would be no difference in this measure. So just as arbitrarily, I could have changed these measurements around and said, well, that we'll call that one a female, and we'll call that one a female, and let's make this one a male, and we'll make this one a male. Okay? It shouldn't change the expected effect of no difference between the two populations. Everybody with me with that concept? Okay. So what you can do then is you can say, well, let's pretend actually that this first subject I scanned was not actually a guy, but was in fact a girl. All right, and let's pretend that this fifth subject I scanned was not actually a woman, but was in fact a guy. So if I change those labels around and calculate the t-statistic again, this time I come up with t equals 0.7. Okay? And I say, well, let's try a different ordering. Let's say, well, maybe this one was a guy and that one was a girl. You change all the labels around again, and you calculate it again. And this time, the t-value comes out to 1.0, or negative 1.0. And you do it again, and this time the t-value equals 0.2, and so on and so forth. Okay? So you try different reorderings of the labels, okay, of male and female, because under the assumption that there really is no difference between the two groups, then it doesn't matter how the labels are set up. And then you make a plot, and you say, well, okay, what does this distribution of t-values look like? Okay, so these are t-values. So after doing all this different randomization and permuting the labels that are assigned to particular values, I might come up with something that looks like this. Okay, a distribution of t-values where, if there really was, if I randomize these labels, most of the t-values I get are going to be pretty close to 0, and just by chance there are going to be some larger values, maybe coming out here to about 1.65 as sort of a relatively big value. And then I look at the actual value that I obtained for the real ordering of the labels. Okay, if I look at the real assignment, right, so I actually remember who was male and who was female, that value came out all the way up here at 3.0. So I'd say it would be very unlikely for it to be the case that there really is no difference between men and women in this measure. Because if I randomize the assignment of male and female, I find that all the t-values that I obtain are smaller than the t-value that I obtained for the actual labeling of male and female. Okay? This is the notion behind a permutation analysis. It allows you to actually, instead of looking up in the back of a textbook and finding out what the distribution of t-values is, you actually go and create the distribution of t-values. In fact, the way that most of those distribution of t-values and the way that the textbooks are designed to kind of come up with these parametric distributions, those have been created by sort of basically, in effect, mathematically doing this computation, kind of creating that permutation distribution and then writing it down in the back of the textbook. Okay? And the reason that, historically people have used parametric statistics and used, formulas and equations to calculate significance is because it's computationally rather difficult. And so back in the day when you just had a slide rule and a piece of paper and a pencil, doing this kind of permutation analysis would have been prohibitively time-consuming. But hey, now that we got cheap computers, this is really easy to do. So as a consequence, this turns out to be probably the best way to calculate significance under most circumstances for statistical tests. Okay? For statistical tests that meet the permutation assumption, which is that you can randomly assign these labels and that you'll be all set. Now, we can imagine some circumstances where doing this permutation would not be valid. Okay? What if it was the case that I scanned 10 men and 10 women, but I scanned all the men during the day and I scanned all the women at night? Okay? If I randomly reassort the labels of male and female, nonetheless I'm not randomizing this other assignment, which is the fact that all the men were scanned during the day and all the women were scanned during the night. So if it was the case that the effect was actually the result of the difference between scanning during the day and scanning during the night, I would still come up with a significant result, even though it wasn't the effect of male and female. So to try and state that in more general terms, to use this permutation approach, you have to have data that satisfies what's called the permutation or equal likelihood assumption, and that is that any one assignment of label would have been equally likely. When a subject walked in the door to be scanned, it is a coin flip. It could have been a man. It could have been a woman. Okay? There's no way that you, as the experimenter, could have predicted who the subject was who was about to walk in the door, right? In terms of time of day or ordering in where they got scanned in the experiment or anything like that. Okay? Yeah?
Do this and you get a p-value that's not different from the one in the textbook. Does that mean you use this?
No, actually. So in general, for very well-behaved data, you should get a p-value that's quite close to the one that's in the textbook. And we'll talk in just a moment about the circumstances will be different and why it turns out to be useful for neuroimaging. That's, I'm about to tell you. Hold on a moment, okay?
Say you didn't have a female group, you just had the male group.
Right.
Compare it to
0. How do you do that? Yeah. So what you do there is you do what's called a signed permutation, where you say, okay, so all I did was I scanned men, right, and I have my 10 values across my population of men, and I want to ask the question, are these values significantly different from 0? Okay? And what you'd say is, well, if it were the case that there really was no effect of my task, right? So if object minus spatial, so imagine I just have male subjects and I calculate object minus spatial, okay? I say, okay, well, if there really was no difference between object and spatial, it really wouldn't matter if I set the contrast up as object minus spatial or spatial minus object, right? Because if there really is no true difference between those, right, the expectation of the difference between the two would be 0. So whether it's spatial minus object or object minus spatial, the average of all that effect should be 0 anyway. So what you do then is you say, well, I'm going to permute then the sign that's assigned to the value. Okay, so in the original version of the data that you acquired, you could imagine each value has been multiplied by the number 1. That is, hasn't been changed. But then, or plus 1. Each value has been multiplied by plus 1. And then you could say, well, let's permute those signs. So we'll say, okay, another possibility is it could have been minus 1, plus 1, minus 1, minus 1, plus 1. Okay, and another one would have been, plus 1, minus 1, minus 1, plus 1, minus 1. So you, in effect, permute the sign of the values. And then see, is it the case that under that random reordering of what amounts to the direction of the subtraction that you made, does that still yield a significant result? Okay, so that's how you do it.
And say you actually did have a group of male, female, so you want to know whether there's a main effect, male showed the effect, female showed the effect, and then you want to know if your groups are different. You would do 3 permutation analyses using
Right.
those 2 things.
Correct. Yeah, so you do multiple permutation analyses, one for each circumstance. Yes?
Do you need to make any assumptions about the distribution or using the t-test and the
No, so now let's talk about some of why you would bother wanting to do a permutation analysis. And so it comes to questions like this. So the first thing is, so if it's the same thing as a textbook, why would you want to do it? Well, it's the same thing as a textbook for the example that I created here, right, where the values happen to be normally distributed. But what if it's the case that you have a very non-normal distribution of values, right? And you can imagine lots of sorts of measures that might have a very non-normal distribution. Reaction time measures, for example, have a very non-normal distribution. So if you were to try and do traditional parametric statistics on that, they'd be sort of invalid to some extent, and the p-values you obtain would be inaccurate. But the truth is, it doesn't matter what the shape of this distribution of reordered values comes out to be. You can still assess it using a permutation distribution. So imagine now instead of t-values, I calculate something else, which is just the absolute difference in percentage signal change between the two conditions. And it has a distribution, that looks like that. Okay, that's the distribution. Well, it's still the case that, my actual value that I observed is up here. And I can say that 95% of the distribution of values was below that value. Okay? So I still have a way of calculating a p-value, even if the distribution is quite unusual. But the reason that this has become a very effective method for use in functional MRI data is the following. In this example, what I've done is I've worked with a single voxel, right? But typically, when we analyze bold fMRI data, we're analyzing data from across a whole brain. And you can imagine analyzing data from your group of subjects. And again, we're trying to look at an entire statistical map of the effect of some task across your population of subjects, okay? And you've calculated a t-value for each point in the brain using sort of just a typical t-statistic. But now you want to try and figure out how to threshold that map so you'll only see those areas that were significantly related to your task across your population, right? And we've already talked about how you would do that traditionally. Is you'd say, well, I want a p of equal to 0.05, but I've got 16,000 voxels, so I need to divide that by 16,000. But wait a minute, this is kind of smooth. You remember that? So it's not really 16,000 independent voxels. Now it's really a little bit closer to 2,000 independent voxels. So it's p of 0.05 divided by 2,000. So I need a t statistic of 7.3 to threshold this thing. Okay? So it turns out that permutation analyses can give you a threshold which is much more lenient than the 7.3 value. So why might that be? Well, so these calculations that sort of assess smoothness and calculate the correction that you need to perform are based upon some assumptions about the data and some measurements from the data, how smooth the data is, how many voxels are there, things like that. And as we sort of alluded to earlier on when we were talking about smoothness, this measurement of smoothness as a full-width half-max measure is approximate, but there's types of smoothness that's present in the data that's not really captured by this. Okay? It turns out if you use a permutation analysis to assess significance of the entire statistical map, you'll take into account all types of smoothness that are present in the data. So even if you don't have an intuition for this, let me just kind of show you practically how this turns out. The way you would do a permutation analysis across whole mapwise data is you say, OK, here's the true ordering of my data. So here are my subject values. And they were 1.2, 3.6, negative 0.1, 1.7, so on and so forth. This was the true ordering. Okay? And when I do the true ordering of subject values and I make my statistical map, I have, the following array of t-values. This t-value here came out to be 3.7. This t-value here was, 1.6. This was 7.3, and so on and so forth across the entire brain. Okay? So that would be one t, or statistical map, that would result from my analysis of the true ordering of the subject data. Everybody with me so far? Okay. So now, though, imagine I say, well, what if I were to reorder this data in some way? Either I do a signed permutation that I alluded to before, or imagine this was data from males and females, and I've now randomized the assignment of male versus female. So I have reordering number 1, and I have some reordering or manipulation of this data, and I calculate the statistical map that's associated with this. Okay? So here's the reordered statistical map, and now the values are as follows. Instead of there being a t-value of 3.7 at this location, now it's negative 0.2. And this t-value is now 0.3, and so on and so forth across the entire brain. And I do this again. Now I have reordering number 2, and I make another statistical map. And I go all the way down until I do, say, 1,000 reorderings, 1,000 different reorderings of the data. Okay? And I then say, OK, across these statistical maps, what was the largest value? What was the single biggest value that was contained in this statistical map? OK, well, the single biggest value here was 7.3. What was the single biggest value that was contained under this reordering of the data? Oh, well, the single biggest value here was 1.7. How about for the next reordering? Oh, OK, well, that was 3.6.
Aren't you taking the same numbers each time and randomly commuting them? So it's a simple.
Well, in this example, I'm doing a signed permutation. So this becomes negative 1.2. This becomes 3.6. This becomes positive 0.1, and so on and so forth. OK, you're good? So you come up with a different set of values, a different set of t-statistics at each voxel each time. OK? So you have the maximum t-value that was seen in each map under each possible reordering or manipulation of the data. OK? And you create that distribution. You say, OK, well, here's the distribution of maximum t-values. OK? And you say, here was my maximum t-value, and here were all the others. OK, so this is 95%. So therefore, so here's my maximum t-value at 7.3, and here is the distribution, and 95% comes out to be here at 4.2. Okay, so the actual ordering of my data yielded the biggest t-value in the statistical map was 7.3, and if I look at the distribution of all maximum t-values that was obtained under all the possible permutations of the data, 95% of the values were less than 4.2. Okay, therefore I can say that on my original statistical map, any value which is greater than 4.2 is significant at a p equals 0.05. Okay? So in effect, what you've done is you've calculated what the threshold is that you need in this statistical map to make it be the case that under all the possible reorderings of the data, all the different experiments you might have conducted, under the null hypothesis, only 5% of the time would there have been even a single voxel which would have turned up on this map above that threshold. Okay? So it's a way, in the end, of calculating what the map-wise threshold is that you need to control the false positive rate for the entire map at a 0.05 level. Yes?
Do you have to have a minimum number of data points in order to use this method?
Right. So the question is that, well, what if I only had 3 measurements? There's only, 3 times 2 times 6 permutations of 3 measurements. So that really wouldn't give me enough permutations to be able to do this. That's right. So you really have to start getting above 10 measurements to really make this permutation possible. Yeah, so once you have above about 10 measurements, you can do the permutation, because you'll have over 1,000 permutations of that. Yeah?
I'm confused by something. I thought you said you're just reordering the map. So that, under that, I thought you were changing around which voxels were where.
No, you're not moving where the voxels are. You're saying, here's the data from a single voxel. Here's what the values were. Now I'm going to reorder those values or manipulate them in some way. And so the data, and so the t-statistic calculated for this reordering of the data at this location is whatever it is now. And now I'm going to do the same process for a different voxel. I've only drawn the reordering values for one voxel here. But imagine I had another whiteboard and I could come on over here and draw the next one over here. Okay, so this would be repeated for every one of the 16,000 voxels. So one thing that anyone who's keeping track at home might realize that if there are 16,000 voxels and I have, a few dozen measurements per voxel, right, and I do 1,000 reorderings of each of those voxels, of which there are 16,000 of them, the amount of total computation here is growing geometrically very rapidly. So this is why this is something which, until only very recently, has been computationally tractable, because we have a cluster of 22 or 25 CPUs up in the CFN analysis center, and if you set up one of these analyses to run on some group subject data, it can take several hours with all the CPUs working full time to try and compute this. Okay, so this is why this is really an approach that's only become feasible with parallel processing and distributed analysis. Okay, we could go into an awful lot of detail about other specific ways that a permutation analysis is better than traditional parametric statistics. Just to highlight a couple points. Permutation analyses avoid a lot of really messy assumptions that had to be made about the data in order to do parametric statistical analyses, particularly in the setting of a cross-subject data analysis. Okay? So you avoid a lot of messy statistics. It provides better statistical values in general. It gives you more power, and it really takes into account it gives you full credit for the smoothness of the map that otherwise you would not get. And there's a bunch of other manipulations, things you can do. The main message that I want to convey to all of you is that if you are analyzing data across subjects, then you really should be analyzing or producing the significance value for that map using a permutation approach. If not, you're throwing away a bunch of power that you could otherwise have. So really, you really should be using a permutation approach. It's really the proper way of analyzing this kind of data. Okay? Any further questions about that? Yeah?
Do you suggest doing that even if, say, you have one ROI you're looking at across 10 people?
Yeah, at that point, the benefit, so the question is, if you're just using one ROI, so in that example experiment where you define, some anatomical region and just look at the effect in that region across your population, would you want to use a permutation approach there? You could still use a permutation approach there, and it still is going to buy you a tiny little bit of benefit. But really, the true power of a permutation approach accrues when you start to deal with these entire map-wise inferences. Okay? It would still be valid in a single voxel or in a single region of interest. It's just the benefit wouldn't be quite as great. But nonetheless, you would have to demonstrate superhuman restraint to analyze your data from a single region of interest and never look at the rest of the brain. So most people are going to end up wanting to do that anyway. Okay? Anything else about permutation analyses? How about group subject analyses in general? Any other questions about that stuff? Okay, we're going to move on. So let's see. And I hope you are preparing questions for the final half an hour, because we will be talking about that kind of stuff. Okay, so now I thought it would be, fun is the right word, to talk a little bit about the different sorts of inferential structures that one can bring to a neuroimaging experiment. So here's where we're going to lead. So for anyone who's been sort of unhappy about descriptions of full width half max and equations and covariates and all that kind of stuff, and has a bit more of a philosophy background, here's where you're really going to come into your own. Because let's talk for a moment about really kind of the philosophy and logic of neuroimaging experiments and about the sorts of things you might be even able to hope to learn by using a neuroimaging experiment. Okay? So just to start the discussion off, let me offer 3 broad ways that one might use a neuroimaging experiment to learn something about the relationship between the brain and behavior. Okay? And if you guys want to add to or debate or discuss these topics, bring it on. Okay, so the 3 big categories that I'm going to offer are localization, implementation, and evocation. These are the labels that I'll assign to these 3 modes of inference. And I'm going to make the argument that just about every neuroimaging experiment is going to fall into one of these categories. Okay? And that once you have a neuroimaging experiment that falls into one of these categories, you're kind of bound by the assumptions and inferential structure that is provided for in one of these categories. So each of these different categories makes different assumptions in order to be able to provide for an interpretation of your experiment and learning something new about the relationship between brain and behavior. Okay? So let's start right at the top, localization. Okay, so this is a sort of fMRI experiment, or neuroimaging experiment, I should say, in general. So, and I think these comments in general apply to PET and fMRI and optical recording and even EEG to some extent. Okay, so localization. It's a very common mode of inference. You've seen it in an awful lot of papers. This is the sort of question that asks, where in the brain does cognitive process X produce activity? Okay? So the idea is that you have a behavior, and in particular you have a particular cognitive process, we'll call it X, and you want to know where in the brain that cognitive process produces neuronal activity. Okay? So the first thing is that we have to identify what we mean by a cognitive process. So what's a cognitive process? All right, well, a cognitive process can be considered as a mental state which is, has some consistent or theoretically relevant properties independent of the particular conditions or tasks which evoke it. Okay? So for example, I can describe the cognitive process or mental operation of working memory, okay? Holding on to information across a brief delay. And I would argue that if the notion of working memory has any sort of utility as far as being a useful concept to discuss in a cognitive neuroscientific standpoint, that working memory would have to be sort of the same kind of thing, whether or not it's evoked by like holding on to the letter A across a delay, or holding on to the letter B across a delay, or holding on to a word across a delay, or holding on to a picture across a delay, right? That there's some sort of unitary concept about holding on to information across a brief delay that exists regardless of the specific instantiation of the task that I use to evoke it. Okay? Everybody with me so far? So you can draw this distinction between tasks and mental operations. And in general, I should say, that when you're thinking about your neuroimaging experiment, when you're thinking about designing an experiment, you really should be thinking about mental operations and cognitive processes and not tasks, right? If you have a task and you say, okay, well, this is the task I want to study, then you're probably not casting your inference at a level which is going to be generalizable enough that other people would be interested in the result too. And I should say that, you know, the early history of fMRI is replete with examples of people who got their hands on a scanner and were a little bit too focused on the task and not focused enough on working or on the cognitive process, right? Where you say, well, look, you know, here's a neuropsychological battery of tests like the Wisconsin card sort and the Stroop test and all this kind of stuff. I'm going to just put someone in the scanner and have them do the Wisconsin card sorting task, which if any of you are familiar with, it involves like these little cards and you're sorting them according to different categories and then the rules change and then you sort them again. And if you actually sat down and thought about it, there's an awful lot of different mental operations that might be involved in that, rendering the interpretation of any one experiment that uses the Wisconsin card sort task maybe a little questionable. Anyway, so you might want to focus on the cognitive process as opposed to the task per se. Okay, but then having said that, now we need to have a way of taking a look at the neural response to a particular cognitive process X. And so to do so, we're going to have a way of uniquely invoking or isolating the cognitive process X, right? So for example, when we come back to that working memory example, you can't just have someone engage in working memory in the absence of having other sorts of things going on. You have to present a stimulus, and you have to have them make a response. Or how about for semantic judgment? I present you a word, and I want you to judge whether or not this word refers to an animal or an inanimate object. Okay? Well, I can't have you engage in the process of retrieval of semantic information without actually having presented you a word, right? Or a picture, or a sound, which is a word, right? And then having you make some kind of response. So this leads to then the notion of that to study a particular cognitive process X, we need to isolate it. And the original and, I guess, most durable way of performing this kind of thing is doing what's called cognitive subtraction. So cognitive subtraction is a mode of inference whereby you try and isolate a particular cognitive process in time. Okay? And the way it's done is you say, all right, look, I'm interested in semantic retrieval. Semantic retrieval, for those who aren't familiar with the term, it means accessing sort of your knowledge about a particular word or a particular concept. Okay? So it requires semantic knowledge to know that the word chicken refers to an animal as opposed to, like, you know, a car that's called a chicken. Okay, so semantic retrieval. So I want to isolate the cognitive process of accessing semantic representations. So to do so, I create a task where, you know, I present a word, and the subject sees the word, and they make a judgment about its semantic content, and then they make a response. Okay? And the part that I'm really interested in is this judgment, this semantic judgment. But all this other messy stuff comes along with it. So I create another task called the control task, which has you seeing a word, right? You see it, and then you make a response. So what kind of thing might that be? Well, I'll put a word up on the screen, and I don't want you to make any kind of semantic judgment about it. Just press one button if it's in uppercase and another button if it's in lowercase. Okay? So I'm making some other decision about the word that's not semantic retrieval. And then I perform my neuroimaging experiment where I have, under one condition, during one period of time, you're performing this task where you're engaging in semantic judgments, and during another time you're performing this task, the so-called control task, that does not contain the cognitive process of semantic judgment. Okay? And then I look at the neuronal activity that differs between the two, and I say, okay, by construction, the only cognitive process or mental operation that differed between the two was the semantic judgment. So therefore, any difference in neuronal activity that I see between the two, I will attribute to the cognitive process of judgment. Okay? So if I have a whole map of the brain, they do the semantic judgment task, they do the control task, I take the difference between them, I threshold my map, and there's a blob here and a blob here, and I say, okay, these are the areas of the brain that are activated by semantic judgment. Okay? That is, in a nutshell, sort of localization inference. So any questions about this as a concept or as a way of doing inference? Yeah?
So many variables that you cannot really control go into targeted control that we find that it's almost hopeless.
Mm-hmm.
Perfectly matched.
Right.
And it's like probably the biggest sort of gray area in the paper that we see. How well. So I'm talking about visual properties, response time, all these items.
Yeah, so Dan chooses to question the assumptions of cognitive subtraction. Interesting.
Well,
no.
As far as how perfect can you make, how perfectly you can control for everything.
Right. Well, so to make a localization inference, to be able to say this area of the brain was activated by the cognitive process of semantic judgment, I have to make the assumption that the only thing that differed between these two things was semantic judgment. Right? If there's some other mental operation that differed between these two, then, well, this blob could have been that other thing. Right? So suppose in this task, I saw the words and they were presented in red letters, and in this task I saw the words and they were presented in, white letters or black letters. Okay? In addition to making a judgment here and not making a judgment here, if I then saw neural activity at this point, right, as a difference between the two, I could say, well, I'm not sure. Was this neural activity the result of seeing red here and not seeing a color here, or was it the result of seeing, performing a semantic judgment and not performing it here? Well, that's obviously a poorly constructed task, and that there's an obvious difference between them. But what I would like to suggest to you, or that might be apparent to you upon further reflection, is that there might be differences between these two conditions, which is greater than that you as an experimenter tried to create. And in fact, this is kind of cuts to the very heart of a limitation of bold fMRI or of neuroimaging in general as a correlative method, in that we attempt to create differences in cognitive processes in mental operations by using particular tasks and instructions and selecting our subjects carefully and all the rest. But in the end, we don't really have control over those things, right? We can't really go in and experimentally manipulate the subject's brain such that they're only doing semantic judgment at that time. Suppose it's the case that, during this task where they're actually making the semantic judgment, they're just a little bit more into it. And when that word comes up and they got to say, chicken or car, they press the button to respond just a little bit harder than during this, admittedly fairly boring task of saying uppercase or lowercase, right? That's all it would take. That's all it would take. Just be a little bit more engaged in this task and press the button a little bit harder because you're a little bit more interested in the task while you're making semantic judgments than during this time when you're not making semantic judgments. Well, hey, all of a sudden now this response is different. The response or motor act here is greater than the response or motor act here. Well, hey, maybe that's the explanation for this blob up here in primary motor cortex. Maybe the subject just pressed the button a little bit harder while they're making semantic judgments. Okay? So the assumption that lies at cognitive subtraction that might be questioned in this way is what's called pure insertion. And this is the notion that you can purely insert a mental operation into an extant set of mental operations without modifying any of the other ones, right? So I can take seeing a word and responding and kind of slip semantic judgment in there without affecting any of the other ones whatsoever, okay? And so cognitive subtraction makes this assumption of pure insertion, that I can slip something in perfectly without affecting other cognitive processes. And in general, this is probably like the weakest point in most neuroimaging experiments that attempt to use a localization inference that exists in the literature. Okay? Any questions, challenges, or concerns about this idea? So just keep it in mind. Now, that's not to say that cognitive subtraction is fatally flawed, should be rejected and never used, and that you should throw away every paper that's ever used it. In fact, for a lot of mental operations, it's really the only thing we can do, right? If you have a mental operation that is evoked in a unitary manner in an all-or-nothing fashion, right? Either you're making a semantic judgment or you're not, then this is really the only way that you could ever try and look at the neural basis of it, okay? A couple other points about a localization type inference. If I see activity here associated with my task, what am I allowed to conclude? I've been careful, or at least I've tried to be careful in the way that I've described the results of this experiment. What I've said is, what you might conclude from a localization experiment is that the mental operation of semantic judgment activates this area of the brain, okay? Notice I have not said that this area of the brain is necessary for the mental operation of semantic judgment, or this area of the brain is involved in the mental operation of semantic judgment, right? In the sense that it's performing something computationally relevant to the processing of semantic information. I can't actually conclude that from a neuroimaging experiment. Why is that? Well, what if it was the case that neuronal activity happens at two sites? When I see a word that is necessary for semantic, I want to perform a semantic judgment, I have two parallel areas of the brain that perform that computation, okay? And then I could go in now and then scoop this area of the brain out, and the subject would be still perfectly able to perform semantic judgment, right? Even though they've lost one of these areas that activated, because this area was sort of a backup area. It was a spare one. Activity in there happened, but wasn't actually necessary for the task, okay? And we could go on about this for a while, and a little bit has been written, and I think in the handout that I gave you, and certainly not if not in there, then in this chapter that I have in the Martha Farah and Todd Feinberg's book on behavioral neurology, I go into a little bit of detail about what exactly is the relationship between lesion studies, like if you make a hole in the brain, and the inferences you can draw from that, and neuroimaging studies and what you can learn about from that. So let me just say in general, so you'll never go wrong if you sort of adopt this stance. If you adopt the stance that a neuroimaging experiment will not tell you whether or not a region of the brain is necessary for cognitive process or not, okay? In the sense that if I lesion it or damage it, will the subject now be unable to do that mental operation, okay? You'll never go wrong if you adopt that as your fallback area of skepticism. Okay, so any questions about that or challenges to that as a notion? Okay, so that's a localization type experiment. And specifically, it's a localization experiment conducted with cognitive subtraction as its method. It's possible to use other ways of performing localization experiments that don't depend quite as directly upon cognitive subtraction, and let me mention one. We've already been exposed to it briefly as we've gone along here, but that's the notion of doing a parametric manipulation. So a parametric manipulation aims to, instead of evoking a cognitive process in an all or none fashion, instead modulate the degree or level of the cognitive process, okay? And here the notion is that instead of saying this is the working memory condition and this is the no working memory condition, instead you have this is level 1 of working memory, this is level 2 of working memory, this is level 3. And you might imagine doing it by saying, here's my experiment where a stimulus comes on the screen, the letter A, there's a delay, and then the box comes up and there's a letter, and you say, all right, was this letter the same as the first letter that was there? That's one task. But then another task is there's 3 letters here, and there's a delay. And then a letter comes up, and you say, was this letter in that array? Okay? And then how about 5 letters? Okay? And the notion is that the more letters you're holding on to across that delay, kind of the more information or the more working memory is being evoked. Your conception of the mental operation of working memory is such that the more letters you hold on to, the more working memory is taking place. Okay? If that's what you're willing to work with, then what you could do is look for areas of the brain where the following relationships holds. Here's bold fMRI signal. Here's the number of letters held across the delay, and you look for areas of the brain that have this kind of relationship. Okay? Such that the more letters you hold on to in memory, the greater the bold fMRI signal, right? Therefore leading you to conclude that there's some relationship between the neuronal activity at this location and the cognitive process of working memory. Okay? So now, all the assumptions or all the questions that you might bring to a cognitive subtraction design can be kind of distilled down and applied in some form to this too. Because you could say, oh, okay, well, when there's 4 items that you're holding onto into memory, when you go to press the button to respond to that, well, that's a little bit more engaging than holding onto 1. 1 was more boring than holding onto 4. So your response is different. So the pure insertion now assumption is now a pure adjustment assumption. That is, I can adjust the level of working memory without affecting the other components on either side of it. Okay? And it's still an assumption, but I think most folks would be willing to accept that as an assumption, it's not quite as strong as the assumption that you need to purely add in a cognitive process without changing anything else around it. Okay? So this is a parametric type design that can be used for a localization experiment. Okay. The next type of mode of inference in neuroimaging experiments is what you might term an implementation experiment. So what's an implementation experiment? This is where you've already decided where in the brain there is activity that's associated with a particular cognitive process, right? So I've already decided that this area of dorsolateral prefrontal cortex has some computationally interesting role to play in working memory. Okay? Now, I want to try and further understand what the relationship is between particular parameters of a cognitive process and neuronal activity in this area. Or, to take an example that was one of the earliest examples of this sort of implementation, suppose I define area MT here, okay? And so I know that's area MT. I can define area MT as an area that responds to motion stimuli, right? And I can make the very strong assumption that area MT is somehow important in the mental operation of processing motion, okay? And I might have this from all sorts of converging evidence, lesion studies, macaque studies of single neurons, and ablation studies, and all the rest. So I say area MT, also known as area V5, that's the area that's responding or processing motion information. Now I want to learn something about how people process motion in the following way. I say, well, you know, there's such a thing as an apparent motion or motion induced by an optical illusion. You know, guys know like the waterfall, like you stare at a screen with sort of like it looks like a sort of a waterfall that you're looking at with something trickling down the screen all the time. And then the screen stops, and now it looks like there's this sort of illusory motion of things moving back up the screen. Okay? And you have a question, is that illusory motion induced by continued activity within area V5 or a suppression of activity in area V5, or what's actually happening there? Okay? And so in that case, what you do is you define area V5. You say, here's area MT. This is the motion area. Now I put subjects in the scanner, and I show them the moving waterfall, and then I stop the waterfall, and I show them a reverse waterfall. And I manipulate sort of the perception of motion in an attempt to try and determine what's the relationship between different parameters of behavior or perception of motion and neuronal activity in this area. Okay? So I'm no longer trying to conclude that this is the area that does motion processing. That's what I'm starting off with as an assumption. Instead, I'm trying to learn about how it does motion processing. Sort of a subtle distinction between a localization hypothesis, but I think one worth making. Any questions about this as a mode of inference? All right. Finally, evocation. So an evocation is really a completely different mode of inference that you might use with neuroimaging experiments. And it's the following. You say, OK, here's an area of the brain, suppose the fusiform face area. And I'm willing to make a rather strong assumption about this area of the brain. I'm going to make the assumption that any time I see neural activity within the FFA, the subject is seeing a face. Okay? It's a very strong assumption. Anytime I measure an increase in neural activity from this area, that necessarily implies that the subject is having the perception of seeing a face. Okay? And I'm now going to use that information to try and learn something about the behavioral state of the subject. For example, I show them this sort of classic, I can't even draw the damn thing, but this sort of vase illusion. Right? So, it's something like this. Okay, so anyway, so you have a vase illusion. It's a drawing which is perceptually metastable. You can look at it and you can either see it as a poorly drawn vase or as a poorly drawn couple of faces. Okay, and it can switch back and forth between these states. And you're interested in learning something about the time course of perceptual metastability. You want to know, you have this notion that perceptual metastability is the competition between two populations of neurons, and you think that if you look at the distribution of time to switch, right, how long you see the face before it breaks down and you see the vase and then switches back. So, time to switch versus the length of time that you're looking at the stimulus. Maybe it has some, you have a theory that it's going to have some decaying exponential relationship like that. Okay, so who knows? Because of some perceptual psychophysical analysis of human behavior, you think that that perceptual metastability has this kind of behavior. Okay, so now you could set the subject up with a keypad, right, and have them look at this picture, and every time it looked like a face, press a button, and every time it looks like a vase, press a button. But you don't want actually anything messy like the subject actually having to decide, which way it's looking. You want to actually be able to know what was the subject perceiving. Were they perceiving a face or a vase without them actually having to tell you? Okay? You want to know, are they seeing a face without them actually having to tell you? Well, you have a way of doing that. You look at the neuronal activity at this location, and you say anytime the neural activity is above this level, they're seeing a face, and anytime it's below this level, you say they're seeing a vase. Okay? And then you put it in the scanner, and you have them stare at this picture, and you measure the neuronal activity from this area, and you get a time course, which might look like this. And you say, great, so now I know. They saw the face during this time, they saw the face during this time, they saw the face during this time, and during this time, and during this time. And I can, now measure these durations and test my hypothesis about perceptual metastability, okay? An evocation type hypothesis. You're using neuronal activity to work backwards to make the reverse inference about what their behavior was or what their mental state was at the particular time the scanning was done, okay? Applied under the right circumstances, and in those cases where the assumption, this rather strong assumption, is well supported, this can be a really powerful method for learning something about behavior and behavioral states. Any questions about this? Yeah?
That assumes that you know what it is for that.
Exactly. It's a strong assumption. So it's clearly the case that there are regions of the brain where this would be a very poor assumption. Here's the dorsolateral prefrontal cortex. Anytime I see activity there, they're in the state of executive control of something or other, and anytime I don't, something else. Well, who knows? There's 1,000 different things that can activate this area of the brain, and it's seen activated in hundreds of different sorts of states. But I might be willing to make this assumption that under the constrained circumstances of this experiment, where the only thing the subject is seeing is either, this vase or this face, that neuronal activity in this site is going to have this particular relationship. And there are ways of sort of like providing some support for this assumption going into your experiment, right? So you could do the experiment first, where you put the subject in the scanner and you positively color this. It's a positive domain, so they see the face or they see the vase strongly for a period of time, and then you put them in and you have them, a period of time where they see the vase or face strongly, right? And so you define the area and say, like, okay, well, look, here's the neuronal activity when I really sort of perceptually drive the system to make it look like a face or drive the system to look like a vase. Now, okay, now let's try the ambiguous condition and see which way it goes under those circumstances, okay? So there are ways that you can provisionally support your assumption in a particular experimental circumstance. But you're right, really the Achilles heel of evocation experiments is this assumption that you know what neuronal activity in a particular location does. And actually, and relevant to sort of the stuff that you've been thinking about, right? I mean, so I would classify sort of studies of deception or sort of the use of fMRI, sort of a lie detector, as being sort of within the evocation category. If neuronal activity present at site X, and I shouldn't say, it doesn't need to be just at site X. You can expand your thinking a little bit about the evocation experiment. Patterns of neuronal activity, temporal networks of neuronal activity. That is, network activity at these 3 locations with a particular time course implies cognitive process X. Okay, so it doesn't have to be just like one region. But so to use fMRI as a lie detector, what you're saying is that neuronal activity at some set of locations with a certain set of relationships between them implies the the mental state of deception or whatever else. Which it's that you could definitely find support for that